The Mach-Zehnder interferometer is a device used to determine the relative phase shift variation between two collimated beams derived by splitting light from a single source. The aim of this experiment is to determine the wavelength of the laser beam and to find the refractive index of the glass plate and to find the refractive index of the air. The experimental setup consists of a diode laser and two beam splitters, two mirrors and three plano-convex lenses. Then a screen, and the interference pattern is captured using a USB camera which is connected behind the screen. In Mach-Zehnder interferometer, the interference is by division of amplitude. Here the collimated beam from the laser source is split into two coherent beams by a beam splitter. The two resulting beams are called test beam and a reference beam. The beam splitter is aligned 45 degrees to the incident laser beam so that the reference beam and the test beam travel mutually perpendicular to each other. Then two half-silvered mirrors are placed in the path of the two beams at opposite sides. The two mirrors are also aligned 45 degrees to the incoming beam. The reference beam reflected from the fixed mirror M1 is then expanded using a plano-convex lens, and the expanded beam reaches the second beam splitter. The test beam coming out from the first beam splitter is then allowed to incident on a second mirror M2. We can move the mirror M2 in a controlled manner by adjusting the micrometer screw attached to the mirror. The reflected test beam from the mirror M2 is expanded using a lens, and the expanded beam reaches the second beam splitter. At the beam splitter, we can see two sets of bright dots. One set comes from the fixed mirror M1 and the other from the movable mirror M2. Then we adjust the angle of the beam splitter until the two sets of dots are as close together as possible. The superimposition of this reference and test beam at the beam splitter result in the interference pattern on two sides which are mutually perpendicular. The interference pattern consists of concentric bright and dark rings. The interference fringes are captured using a USB camera which is placed behind the screen. If there is a change in the optical path length of the beam, it will result in the fringe shift. The optical path length can be altered either by changing the physical path length or by changing the refractive index of the medium.